So it's 10 year now. So we're having a 10-year anniversary event at the SES meeting in Hangzhou this year.
Yeah, Qingda told me about that. Yeah.
Yeah. Okay.
I will attend to the SES. Yeah. Maybe we can meet a lot of friends there.
Qingda, so how did you log into the Zoom webinar? Did you use the Zoom link?
Yes.
Because I just sent the Zoom link to Zhigang on WeChat, and he told me he cannot get on.
Okay.
I don't know.
I used the link. Okay, the link was just the one that you provided.
Yeah.
I also use the
That's
link.
the only Zoom link we have.
This is https :ter.ps/EML Webinars S2.
Exactly. It's weird.
Let me send him an email. Hold on. Yeah.
Oh, Zhigang, I think he logged in eventually. Let me promote him to the panelist.
Wow. Why it didn't?
Hi, Zhigang. Good morning.
Hey, good morning. The camera seemed to be in the wrong direction. Why is this Zoom so unusual? Let's see. This Zoom is so unusual. Zhigang Suo, same as system. Start a camera, same as system. Mirror my video. Blur my background. What else?
The camera is not pointing to your face. It's pointing to the desk. Are you using a laptop, Zhigang?
Yeah, I'm using a laptop.
Okay, flip the laptop up, maybe to see what happens.
Flip the camera somehow it doesn't select Zhigang's iPhone camera. FaceTime. All right. Oh, okay, good. All right.
Nice. Okay.
So, well, then other people must have difficulty to log in. It took me many clicks to log into this.
Oh, wow. That's interesting. I didn't have any trouble logging in from Singapore.
From Singapore. All right.
Mm-hmm.
Yeah. Many clicks.
All right.
I even have to download something. I use Zoom every day, multiple times, but this Zoom link somehow, I don't know what happened. Is this new?
No, we've been using that for the past several years.
Oh, okay. Yeah, I think next time I will test the Zoom link with my students before next EML webinar.
All right. Okay.
So Zhigang, you want to start the interview process?
Oh, an interview process. Okay. All right. I forgot that's our procedure. All right. Yeah.
Really?
Okay. Also, today's our speaker is Tongqing Lu. Tongqing.
Yeah.
Tongqing. So I start the interview. Actually, I actually don't know which where were you born?
Where was my born? Yeah, in Shandong province, China.
Shandong province.
Yes.
From Shandong.
Mountain Tai. Do you know Mountain Tai? Just at the foot of Mountain Tai.
Okay, Mountain Tai. So and then you went to Jiaotong University. Which year?
2003. 2003.
2003.
Yes.
I see. So then 2003 to 2007, you graduated 2007. Then you became
another 6 years. I got a PhD degree in 2013. So I stayed in Xi'an Jiaotong University for 10 years for my from bachelor degree to PhD degree. 10 years.
10 years. That's right.
Oh, but yeah, during this time, 2 years at Harvard.
Yeah, at Harvard in my group. That I remember. Which year were you in at Harvard?
2010. Yeah, to 2012.
All right. Yeah. Oh, I see other people. Other people are Robin.
Hi, I see Robin.
Robin, hi. Robin, can you unmute? Robin.
Hello, Robin.
Yeah. Oh, Robin. Okay. All right. So, okay, we'll let Robin figure out his situation. All right. So, Tongqing, so how did you select at undergraduate level when you enter college? How did you select mechanics as your concentration, your major?
The reason is in the high school I like physics actually, so I thought mechanics is just a kind of physics. That's the first reason. The second reason is at that year, Xi'an Jiaotong University, if you select this major, you will enter the master degree without examination. So then if you have a higher score, then you have the chance to select this major. So that I think that's the main reason.
So this option, automatic become master student, was only available for certain concentrations.
Yes, if I remember right, only 2 majors in Xi'an Jiaotong University have this such option.
Yeah. So then, after you have your degree in college degree, bachelor degree, you enter graduate study. Who was your thesis advisor?
Professor Qiejun Wang.
Qiejun. Yeah, I remember that. Okay. So, what was your PhD thesis topic?
It's dielectric elastomer.
Oh, okay. Is there something you did with me? But I did something with Professor Qiejun Wang. What was the topic then with him?
Is thermal barrier coatings, the mechanical property of thermal barrier coatings, also solid mechanics. Yeah.
So then your thesis was focused on dielectric elastomer.
Yes. And the previous works related to thermal barrier coatings just remove all of that part.
Okay, right. Yeah. Robin, I have a question for you.
Oh, you have a question for me?
Yeah.
Hi, Tongqing.
Yeah. Do you sign in this Zoom call easily?
my trick is I go to iMechanica and then there's a link. Otherwise, I'm gonna need to type in my link.
Oh, so and it's just one link you sign in. Somehow this morning it took me many links, many clicks to sign in to this webinar. Maybe it's just something happened on my computer. Don't know. Okay, all right. Okay, Tongqing, back to Tongqing. So after you got PhD, what happened to your career?
Oh, without postdoc, I just stay in Xi'an Jiaotong University as I think it is called assistant professor or lecturer. Yeah.
So you didn't have a postdoctoral experience?
No. At that time, I remember you suggest me to do a postdoc. But
Oh, I did?
yeah, and Tiejun suggests me that because at that time, without postdoc, you can stay as in the university as an assistant professor. So I just did that.
You did that. Was that a good idea?
I don't know because the first few years as assistant professor, I think I did very similar thing as a postdoc because I did not need to teach, so it almost no difference as a postdoc.
Yeah.
Yes.
Now my understanding is now you are an associate dean for something. For what? Associate dean for?
Yeah, for School of Aerospace Engineering. Yes.
Yeah, but what's your responsibility?
Yeah, the first thing is to recruit people. Second is international communications, including the between the faculties or and between the students, exchange student, international exchange student. Yes, and some other things. Yeah.
So about the recruiting faculty, young faculty, right?
Mhm.
So your responsibility is to recruit people from outside China or within China or everybody.
Most out of China. Yeah, within China is our dean is responsible for that. So I was particularly responsible for recruiting people from outside China. Yeah, but most people still Chinese, Chinese outside China. Yes.
So I understand that Xi'an Jiaotong University is a leading university, but you must have a lot of competitors where you try to recruit from outside China. Who are your main competitors?
Yeah. Yeah. In recent years, maybe Beijing University. Yeah, Peking University, and Zhejiang University, I think. Yeah,
So,
because Tsinghua University, yeah, they're limited to recruit people, so it's not not a competitor.
although Xi'an University is not a competitor, they cut themselves out. That's very interesting. So now also I interact with you over the years. So in Xi'an Jiaotong University, you guys have built a platform to do soft material research.
Mhm.
So how many young people are young faculty members are working on polymers, gels, this kind of thing? Mechanics mostly.
Mechanics, me, Jingda, Zhengjing, Jia Kun, and recently Guo Gao, yeah, maybe, and Gaoyang, Hu Jian, yeah, maybe 6 or 7, yeah. But you know, Hu Jian and Gaoyang, they are from their background polymer materials, yeah, material science, and the mechanics background maybe 4 to 5 people, young people.
Yeah. because you probably recognize this is a very unusual in other parts of the world, have several very good, strong young people working on similar field on the same campus. So you also have yourself have international experience. What do you think? Why in on your campus you can accommodate quite a few people, very strong people in the same field? What makes that happen?
The reason is simple. Because of you. Yeah, because of you, of course. Yeah, because this lab was established based on your influence. So many people like Hu Jian was recommended by his supervisor, Professor Jianping Gong. Yeah, also has some relation with you. Yeah. So, and here, these people, most of them have the background from your group, study in your group. So they want to get back to join this lab to work together.
So also this is unusual. Yeah, I think I know the answer, but probably because you are now also in the leadership position. Several young people, strong young people in the close related field. How do you find a way to, I guess, synergize or maybe some competition? How do you guys think about this?
Yeah, there's maybe there's no competition, but there's some trouble if you want to present out of Xi'an Jiaotong University, just within China, maybe not international. People will feel you do very similar things from different people from the same university. I think we ourselves just want to find our own ways. For example, recently I worked with you on the project of high throughput experiment. Maybe other people are focusing on something else. So I think we ourselves should find a way to avoid such trouble. Yes.
Okay. Then do you also sense some benefit of having close colleague working on similar things?
Yes, I think the benefit is much more than the trouble. So that's why we like to work together in the same lab.
So Jimmy, at this point, do you want to? No, it's already 10 o'clock.
Yes.
Yes.
Jimmy, do you want to say a few words? Jimmy Xia is the leader of EML. Please say something.
Yeah. So just a couple of things I want to mention. First of all, this EML webinar series, the credit goes to Zhigang. Actually, this was started an idea from Zhigang during the pandemic when everybody was stuck at home, and he came up with this idea that we cannot see each other at conferences. At least we can see each other online. So thank you very much, Zhigang, for the wonderful idea. And now we're providing a platform for younger generation to present their work. And I think it's very exciting. Older people, Zhigang can attest that statement, receive all kinds of invitations to present webinars all the time. But I think we are maybe one of the first to provide the platform for young people to do that. Another thing I want to mention is 2024 is the 10th anniversary for EML, for extreme mechanics letters. So we're having a couple of events. One is a special symposium at the Society of Engineering Science meeting, SES meeting 2024 in August of this year in Hangzhou, China. The other one is we're planning to other activities. We're planning to have a special issue dedicated to the 10-year anniversary. Okay, that's all. All right.
All right.
Going back to you,
Let's-
Zhigang.
Okay, thank you, Jimmy. And thank you, Zhen Jia, for being a host. So let's just move to Tongqing. Tongqing, are you ready to share your screen?
Oh, yes. Mhm. Okay, so can you see my screen?
Not yet.
I can.
Okay. Oh, now you can see my screen. Okay.
Yes.
Somehow I cannot see the screen. Huh? It's just maybe just my meeting, my problem. So Tongqing, why don't you just start?
Oh, okay. But it's still considered.
I cannot see it.
Mhm.
What about
Okay.
others? Okay, so let me ask a few people. Daniel, can you
Yeah.
see? Yes, okay.
Yes, I can see it.
All right, good. So
All right.
Dan is from Penn State, so it's at least from United States.
Okay.
We can-
All right. Tongqing, why don't you get started? I'll try to figure that
Okay.
out. All right.
Okay, yeah. Thank you. So I will start. Okay, thank you very much. Thank EML for giving me this opportunity to present our recent work. So I'm Tongqing Lu from Xi'an Jiaotong University, China. So today my topic is high throughput rupture experiments of soft materials. Okay, the first is background and motivation. In the last few years, I have been working with Zhigang to study the fatigue of hydrogels. So to characterize fatigue, there's two standard types of fatigue tests. So the first type is the left one, is we put a precut to the sample and apply a cyclic load. And we record the cut growth per cycle as a function of energy release rate. So it's called GdCdN curve. So we have two limits on this curve, toughness and threshold. So this method has been used widely in recent years to characterize fatigue of hydrogels. The other type is we apply cyclic load to a sample without precut. We apply a stretch amplitude and record the number of cycles to rupture. So this is called lambda n curve. This is another type. And in this work, I collaborated with Zhigang. We use this type of fatigue test to characterize the fatigue of hydrogels. So for the lambda n curve, actually there's a feature in this curve. So for a given stretch amplitude, usually the number of cycles to rupture will differ from sample to sample. That means that there's a wide scatter in such curves. Yeah, if you are familiar with the fatigue test, it's a common phenomenon. So when the student, Yifan Zhou, was doing this experiment, he made a little innovation. So he clamped 6 samples in parallel and stretched them simultaneously. Because we only need to measure or record stretch, so we do not need to measure stress. Okay, of course, in this paper, we focus on to study the flow sensitivity of the material under cyclic load, but this is irrelevant to today's topic. So with this parallel fatigue test, so we can obtain the lambda n curve. So for any given stretch amplitude, we can obtain 6 data points just from one round of experiment. So at another fixed amplitude, we can get another 6 points. So when we get all these points, we can imagine the time for the fatigue test. can be reduced by almost 6 times. Okay. So that's the idea. So from the 1 sample to 6 samples. So one day, Zhigang just asked the question if we could do more samples. Okay, so that's the basic background and motivation. So before we do the high throughput experiment, we did a little literature review. We found that about 90 years ago, there's a guy named Cooper who did exactly the very similar experimental setup as we did. So this is a prototype of the parallel mechanical test also for the fatigue rubbers, and even the number of samples is exactly the same. And also later we found that in some companies then fabricate the tensor machines. Then machines can also stretch multiple samples to test the fatigue property. But the number of specimens is still small, usually between 10 to 20. Okay, so we just do simple extensions from 1 to 6, then we extend to 1,000 samples. So here's the schematic of our high throughput rupture experimental setup. So three things. The first, we use 3D printing to prepare the massive samples nominally in the same condition. So in this experiment, we prepared 1,000 samples with 5 rows uniformly distributed. The material is epoxy. Okay, it's a soft material. So second, we fabricate a loading mechanism with 1 degree of freedom that can pull the samples to the same stretch simultaneously. And third, here we have a camera here to record all the deformation process and identify rupture by image processing. Yeah, because the material is soft, so the deformation is large and easy to record by image. Okay, so here's the photo of our experimental setup. So we use a computer to control the electric displacement table to apply load to these samples. So here's the sample region. So the 1,000 samples, each sample is of this size, is about 1.5 millimeter in width. So the camera was used to record or to videotape all the experimental process. So we first do the monotonic loading to rupture. So in the reference state, 1,000 samples, 0 sample ruptures. So when we apply a stretch to 1.8, we can see 34 samples have ruptures at different locations. So when the stretch is 2.2, more than 900 samples have ruptured. Okay. So here's the experimental results of the monotonic loading or monotonic rupture experiment. So the 4 lines means we do 4 rounds of experiment. Each round of experiment, we have 100 or 1,000 data points. So the vertical axis is called cumulative distribution function. Yeah, it's short for CDF. So CDF just means the fraction of rupture samples. For example, if you apply a stretch to 1.9 something, the CDF is 20%. Means the 20% samples out of the 1,000 samples have ruptured at this stretch. Okay, so CDF just means the fraction. So after collecting all the 4,000 data points, we can do some Weibull fit, yeah, and obtain some fitting parameters. So we will talk about the fitting in details later. Okay, here's a cyclic load, the value of the cyclic load. So it's 1,000 samples and given a specified stretch amplitude, they just do cycles. And at a certain cycle, we can record or we can identify how many samples have ruptured at a given cycle. So here are some snapshots from the cyclic loading. So for example, at a given stretch amplitude 1.6, so you can see as the cycles increases, more and more samples rupture. At another stretch amplitude, for example, 1.9, you can see all the samples can only survive about 1,000 cycles. Okay, so we can collect all the fatigue data. The first we can plot on the traditional lambda n plane. So for a given lambda, you have many number of cycles, 1,000 points here. Because the points are so many, then we cannot see the scatter very clearly. So we still prefer to present the results on this CDF plane as a function of the number of cycles to rupture. So once again, this CDF means, for example, if you apply 100 cycles, maybe 60% of the samples out of the 1,000 samples have ruptured. Okay. So now we have a very large data set on rupture or fatigue fracture. So what can we do with this data? So one thing we can do with this data set is we can use that to predict rare event rupture. So rare event rupture means the rupture occurs at a very low probability, say 1% rare event rupture. For example, in engineering applications, for example, there's many gas turbine blades, many. So the engineers care much about the strength of the weakest blade rather than the average strength of the blade. So maybe only 1 or 2 blades will rupture at a rare event. So then what does rare event mean? But also, for example, another example is like the aircraft crash. Of course, it's also very low probability, but it's of great importance in practical applications. So how to predict the rare event rupture from our large data set? So because we plotted a CDF as a function stretch, so rare event just means low CDF, because CDF just means fraction. So here the fraction is 20%. So here, for example, the 1.7 something, the CDF can be very low. So this is the rare event rupture stretch. Okay, if we zoom this out, so the right figure is just a zoom out. So the vertical axis goes up to 1%. So this is a rare event region. Okay, so to predict the rare event rupture, of course, we need to do some Weibull fitting because experimental data discrete. So we want to fit to have a continuous line to predict any event. But here, when we do fitting, actually there's a trick here. So if you use the whole data set to fit, you will see the fitting is not good, actually. Our collaborator, Professor Jose from Stanford University, they taught us a way for better fitting. The idea is just use the local data set to fit. For example, from the 4,000 rupture data, we use the first 200 data to fit. Then we get a very good fitting. Okay, so we will not go about the details. So in this figure, the red dots are experimental data. The solid line is our Weibull fitting, and the 2 dashed lines are the 95% confidence bound. Okay, so let's look at the rare event. For example, the blue line. This is 0.1% rare event, which means because this is 4,000 samples, So 0.1% rare event means the first 4 samples to have rupture. Okay, so you can see all the experimental data falls within the 95 confidence bound, means the Weibull prediction accurately predict this rare event happens between these 2 stretches. You can see, so very accurate prediction. So here's the prediction for rare event fatigue fracture. So this is the original data with different stretch amplitude. We use one curve and just zoom out. This goes to 1% rare event. Once again, we use a local data set to fit to get a better fitting result. So we can see the dashed lines predict the 90% confidence interval, means the 1% rare event fracture, a fatigue fracture will happen between the cycle 480 to 700. And the experimental data, the 1% means from the 1,000 sample, the first 10 samples have undergone fatigue fracture. So at the cycle 400, once again, very accurate prediction. So in practical applications, of course, it's not often to have such a large data set. Usually people just have a few dozens of samples to do fatigue test. So to mimic this, we randomly select 50 data out of our large data set. We do this random selection 3 times randomly. So you can see the 3 results shows clear inconsistency, right? Sometimes you can see it just totally fail to predict. And sometimes the predict confidence interval is too wide to use. And sometimes if you are lucky enough, you can also get a good prediction. So that means using a very small data set to predict the rare event fatigue fracture is rather unreliable. Okay, so this study we reaffirmed that predicting rare events requires very large data sets. So our development of the high throughput experiment setup, of course, is really important. Okay, so next I want to talk about the data quality of our high throughput experiment. So the title is called Detection and Reduction of Systematic Bias. So look at our experimental photo. So the Professor Jose, our collaborator, when he saw this figure, he immediately pointed out, so see there's bias. See the samples in the bottom row, many samples have not ruptured, but you can see the samples at the top row, most of the samples have already ruptured. So there's bias in this experiment. So how to evaluate this bias or the data consistency? So they taught us a mathematical method called AD test to do this. So the idea is we first divide the total data set into subsets with different columns, different rows. And for each subset, we can calculate a statistical distribution. And we use this little formula to compare the closeness between different pairs. Between the we calculate the closeness of the distribution among the different pairs of subsets. So then we get a p-value, a p-value. So if the p-value is large, that means these 2 subsets are very close. The distribution are very close. But if the p-value is small, that means the 2 distributions are not close. So our calculation find that almost the different rows, the p-value is near 0. that means the closeness between different subsets are terrible in our first generation experimental results. This is different rows, this is different columns. Okay. However, this method gives us is very helpful for us to find out the sources of the systematic bias. Yeah, for example, if you compare this region and this region, if you find these two are very close, but not close to the middle part, that may indicate the bar is bent, right? If you compare this row with this row, you find they are not close. They may indicate that the displacement applied is not even, right? So with that, now we can identify three main sources of bias: insufficient rigidity, insufficient
I understand.
Insufficient surface friction and uneven displacement. Now we can improve our experimental setup by resolving all the three issues. Now we update to the second generation of our experimental setup.
Poo on Tongqing. I shit my pants.
Okay, so with the new setup, the data consistency has been greatly improved. So this is our new experimental setup. Apply different stretches. So different columns. So you can see almost different subsets, different regions ruptured as almost uniformly, right? And also we can use this AD test to calculate the p-values between different columns. And you can see the p-values is much larger than before, which means each two columns have very close distributions. Also, we repeat the experiment 5 times and plot the data from the 5 experiments together, and we can calculate the closeness between the 5 experiments. Also, we get a large value of p, which means with the new experimental setup, the repeatability of this setup is very good. Okay, so now we have the new data and the old data. We can easily compare the difference between these two data. So first, if we use the data set to fit Weibull distribution, we can see the old data, the fitting is not good, but the new data, the fitting is much better. And if we use the data to predict the rare event fatigue. Yeah, you remember previously, if we use 1,000 samples to predict a rare event, the prediction is okay. But if we use 200 samples with the old data, you can see the prediction is rather poor. Yeah, is rather poor. But with the new data, yeah, with the new experimental setup, we can see even we use only 200 samples, the prediction is much better and it's very stable. We can repeatedly do this analysis 6 times, randomly selecting, and each time we get a very good prediction. So of course, the new data is gives much better prediction than the old data. So to summarize on the data quality, the discussion on the data quality, we found that the systematic bias in a high throughput experiment is very commonly observed. So this bias may come from different people or different time. So our study indicate that if you collect data from very different sources, and we cannot rely on such kind of data set to give very accurate prediction on the statistical properties. So we suggest a general procedure to improve the data quality of in a high throughput experiment. So first run the experiment and then use a statistical method to test. then this test may help us to find out the sources of the systematic bias in the setup, and then improve the setup and iterate. Okay, so next we want to talk about the data quantity of our high throughput experimental data set. The data quantity means, so now we have a large data set, but how large is large enough to accurately estimate a statistic? So give an example. For example, if now I have a data set of 5 data, the data can be strength or rupture stretch or any mechanical property. So from the 5 data, we have average. So imagine if I repeat the experiment to get another 5 data, then I get another average. Of course, these 2 averages may not be the same because we have the experiments then, because the strengths have a large scatter, right? These 2 averages may not be the same. But if we increase the data set, the number of tested specimen, we get another average, 20 or 100. So imagine in a hypothetical experiment, if we can test infinitely large number of specimens, so we get what they call true population, right? And we can get a true average. Okay. So the question is, how different are these values? How different between mu1 and mu2? How different between mu1 and mu4 and the true average, right? So now we have a large data set, maybe 100 or 1,000, but is the 100 data is large enough to accurately estimate a statistic to approach the true statistic? Of course, average is just one statistic. Other statistics include, for example, standard deviation and quantiles and so on. So now we conducted another high throughput experiment. So here we use silicon rubber. Yeah, we also measure the rupture stretch of the 160 silicon rubber specimen. So here we use laser cutter to prepare the samples, which is also very efficient way. So we have this CDF as a function of stretch, so 160 points here. Now we use this point to test if this is good enough to estimate a statistic. So now we need a new statistical method called bootstrap method. Also, the Professor Jose teach us. So this method is used to calculate the confidence interval of a statistic. So the procedure is the following. So we have the original experimental data set, for example, 160 rupture stretch. Now from this original data set, we generate many bootstrap data sets. So each bootstrap data set is generated by randomly selecting the specimens from the original data set with equal probability. But note that we allow repetition. Yeah, means if for example, if in this bootstrap data set, I put this here, and in the next selection, I put it back. Yeah, allow repetition. So now I can have as many as I want bootstrap data sets, for example, 40 or 100. Okay, and each bootstrap data set will generate a statistic, for example, an average value. So we put all these statistic values on this as dots on this line. So here I put 40 dots. So removing the 4 red dots, the leftmost 2 dots and the rightmost 2 dots. So the remaining is 90% confidence interval. Okay, so this is I feel this procedure is rather magical because you only have one original data sets, but we generate like 40 fake data sets, and each fake data set give one fake average, and this average gives us a confidence interval. So that's the procedure. Okay, so we then use this bootstrap method to our original data. So this is the original data set. So we generate 40 bootstrap data sets. So here just to show 2 representative bootstrap data set. You can see they're similar to the original one, but they're not the same. Okay, so the 40 bootstrap data set generate 40 averages. They are plotted on this line. Remove these 2 and remove these 2, so the remaining is the 90% confidence interval. So the average is of the original data set is 4.77, and this confidence interval is this. So the confidence interval means if you do a high throughput experiment with 160 samples, you will get an average in this range with 90% confidence. Yeah, that's what the confidence interval means. Okay, now next we examine the effect of a number of specimens on the confidence interval. Yeah, it is easy to expect that if the number of specimens is larger, so the predicted confidence interval is narrow. It's narrow. Okay. For example, here, if the number of specimens is 10, the confidence interval is this range. Okay, so whether a confidence interval is good enough, it depends on the practical applications. For example, this is the confidence interval for the rupture stretch of silicon rubber. If you feel this confidence interval, this range is narrow enough, so that means the 10 specimens is good enough. But if you want to narrow this confidence interval, you need more specimens, you need more data set. So that's the idea. So the bootstrap analysis can quantify the size of the experimental data set required for an accurate estimate of any statistic. So here, average is just an example. So for other statistics, for example, standard deviation or coefficient of variation, we can do the similar things. Yeah, for quantile, so we use the bootstrap method to determine the confidence interval for 50% quantile, 10% quantile, and 1.25% quantile. So we can see with the 160 rupture data, so the predicted quantile, predicted 50 quantile, this confidence interval is a very good, accurate prediction. But for the extremely low quantile, we can see the prediction is rather poor, right? This means even with the same number of data, you can predict this statistic very well, but you cannot predict the extremely low or extremely high quantile. Another example is we change the material. We find in literature, we collect the data of strengths of ceramics of 33 specimens, 33 data. Okay, we use the bootstrap method to determine the 90% confidence interval. So the average value of this 33 specimens is 860 megapascal. And the confidence interval is this range. So here we can compare the weights of this confidence interval is 190. And the ratio between the weights and the average is about 0.22. Okay. As comparison, if we use the rupture stretches of 33 silicon specimens, the data from our experiment, we can calculate the average is this number and the confidence interval is this range. And you can see the weights divided by the average is very small compared to ceramics. So this means if you have like 30 specimens, you can give very accurate prediction on the confidence interval for silicon rubber. But if you only have 30 specimens, the prediction for the strength of ceramics is rather poor. Okay. Of course, here is also reflect that the ceramics is more flow sensitive than the silicon rubber. Okay, so now to summarize the discussion on the data quantity. So we have a large data set, but how large is large enough? Actually, this answer is a little complicated. So it depends. First, the statistic itself. For example, for the same number of same size of experimental data set, to predict average maybe is good or is enough, but to predict extremely low punctile is not enough. Okay, and this answer also depends on how much the random variable scatters. For example, for example, 30 data. And maybe it's good enough to predict the strength of rubber, but not good enough to predict the strength of ceramics. Okay. So with this study, we can see that because in the standard, for example, ASTM standard, the standard suggests us in the strength test, they usually suggest the test number of specimens is between 6 to 10. Okay, but our study showed that this common practice of using small data sets to estimate statistics should be reconsidered. Okay, of course, hopefully, if one day this high throughput experimental method can be widely adopted, of course, the standard should be changed. Okay, so that's all for the discussion about the large data set and the discussion on the data quality and the data quantity. Yeah, so this discussion about statistics is very helpful for us to establish a very standard way to do high throughput experiment. Yeah, but also maybe it's a little painful to understand. But our group also is developing more experimental setup, high throughput experimental setup to do more types of mechanics experiment. For example, in the beginning, we say there's two types of fatigue test. We focus on the right one. For the left one, we can also develop a high throughput experiment. It's very simple. So yeah, in traditional, when people measure the GDC-DN curve, people usually use the pure share configurations. Yeah, but to do the high throughput experiment, we need to choose this single edge notch specimen. The energy release rate for this configuration is here, because this kind of configuration is easy to arranged in a parallel way. So here we arranged claimed 10 specimens in parallel, with each specimen having the different pre-cut crack length. Means when we apply the same stretch, each specimen is subject to a different energy release rate. In fact, it may not be called high throughput because we only have 10 specimens, but we found out 10 specimens actually is enough. Yeah, let's say the experimental, for one run of experiment, you can see the cyclic load, yeah, the number of cycles, and the specimens rupture one by one. We record the crack growth for each specimen as a function of the number of cycles. And we get this GDC-DN curve. So note that with just one run of experiment with a given stretch amplitude, we can obtain almost 100 data points on this plane. So traditionally, using pure share configuration, for one run of experiment, we can only get 1 data points on this plane. It's very efficient. So after 2 runs of experiment, yeah, one experiment with a stretch amplitude 1.2, the other is 1.7. So we can see we almost obtain a complete fatigue crack growth rate curve, including the toughness and the threshold. Okay, only 2 rounds of experiment. So if we do more rounds of experiment, for example, 5 rounds, we have a lot more data here, and the prediction could be a little more accurate. So note here, this figure also includes 4 triangles. The triangles means the data point were obtained by traditional pure share test. So yeah, this 4 data point calls for 4 rounds of experiment, and all the other data points are from the 5 rounds of high throughput experiment. So we can see with this setup, just with a few rounds of experiment, FCGR curve, the fatigue crack growth rate curve can be obtained. Okay, this is the last page. Just briefly introduce our ongoing work. So now we are developing the 2nd generation of experimental setup we update to the 3rd generation. So the student Wu Hou is doing that. So this update is very important and powerful. So in this generation, now we can measure stress. So now both stress and strain can be measured for each individual node example, which means if you do 1 round of experiment, you can generate a lot of stress strain curves. And with this setup, we can do a lot more. Okay, so that's the end for my talk. So acknowledgements, of course, first a special thanks to Zhigang, who guides us to this very exciting field about the high throughput mechanics experiment. We feel there's a lot of things can be explored, a very exciting field. And Professor Jose from Stanford, he and his students gave us great support in the statistical analysis of our data sets. And also some students from my group, they were doing experiment. And the experiment were done in the soft machine lab in Xi'an Jiaotong University, and I thank the funding agency, NSFC. Okay, thank you. Thanks for your attention.
All right. Thank you, Tongqing. Can you please unshare your screen so that we can see the audience? Excellent.
Okay.
Now, question from the audience. Anybody? Oh, all right. Robin, go ahead.
Thank you. That was a lovely topic. Very interesting. So I have a rather general question. So I thought, correct me if I'm wrong, it's like you did an experiment and then you found something. The statistical analysis is somewhat ad hoc, and then you find something not in a good agreement, and then it guides you to further improve the experiment. I'm wondering if there is any opportunity. Could you share some insight into where can we have some theory or statistical theory or uncertainty quantification? That's a big field as well. How can we use that to guide the experiment design rather than we first try the experiment and then have an ad hoc approach? I don't know if I understood that correctly, but could you share some thought on that? Thank you.
Okay, thank you, Robin. Very good question. From our experience, I think we cannot totally rely on, maybe not, we cannot say we cannot, but from our experience, we did not totally rely on the guidance calculated for example, from the p-value, from this statistical method. So actually, we have some feelings first about the possible reasons of the sources of the bias. Then we can, with this source, we can just check, use a mathematical tool to check. Of course, so these 2 kinds of method, maybe sometimes one go first, sometimes I don't know if we have a standard procedure, I think, or a general theory to do that. Yeah, it's a combination, I think, between both. Yeah. But our experiments did show that if you find these two rows, the p-values are small, but the p-values between columns are large, that's clearly indicate, yeah, maybe the even displacement of you apply is not very good, but within the row it's okay. So some evidence, yeah, there's some evidence, but not always. Yeah.
So a general response, Robin, is a good question. So now in mechanics materials, it seems that high throughput experiment is actually not very common. There must be other examples people should talk about their own experience, but relatively few compared to, for example, chemistry, compared to electronics. Anytime you do electronics transistor, people test many samples. Supposedly, it's because testing samples mechanically in parallel itself is a challenge. However, in terms of statistical analysis, maybe we can learn a lot from other areas where people have more experience to do parallel experiments. I see Daniel is here. In biology, I don't know if you guys sample cells, maybe there are large population. Daniel, do you want to say something about high throughput experiment, meaning many samples simultaneously observed, tested? Is that common experience?
So a high throughput, yeah, mostly it's for screening. There's a lot of high throughput experiments. So the typical high throughput experiment might be you sow out a library of genetic variants of a plant or an organism, and then you grow them up under certain conditions, and then look for a change in the morphology of the material or the ability to grow. And sometimes you'll challenge them with chemicals that modify some aspect of the development, inhibitors of some sort or another. That's another case where that happens. Another kind of high throughput thing is with individual cell cultures. What can be done is they can do some genetic tricks so that under certain conditions, fluorescent protein is produced, and then they can run these cells that may or may not be expressing this fluorescent protein. They can run it through a cell sorter. So one by one, the cells but very rapidly, the cells are drawn through a stream and then kicked one way or another, or counted at least. And one can get millions of cells.
Thank
counted.
you, Daniel. Yeah, Jimmy, yeah, you raise your hand.
Yeah. Okay. As I maybe ask the question, Tongqing, can I ask you to put up your slides again?
Oh, okay.
Okay. Especially the first video that you showed. So first of all, very interesting talk, actually. I specifically appreciate your statement that some of the ASTM standards may need to be revised or improved.
Okay, this fatigue
test. Fatigue, right? The fatigue one, the movie.
Okay, this one.
There's another one. Okay, maybe, but there's another one. I see some. Okay, so yes, this is the one. So for one particular loading cycle, that loading cycle as well, I see some of the the samples are relaxed, they undergo buckling. Okay.
Yeah.
So here's my question. What type of fatigue loading that you apply? You apply controlled displacement, did you?
Yes.
Okay, so it's not load controlled, it's displacement controlled.
Yes, the displacement control.
When you do the displacement controlled, did you do it in the tension cyclic loading or tension zero? The displacement can be controlled to load it to a certain value, then go back to zero, load it to a certain value, go back. What is the condition that you apply?
Okay. Thank you. Thank you for the question, Jamie. So we do the minimum stretch is lambda equal to 1, and the maximum stretch is a specific number of stretch. So
it's
we
tension
tend to
zero,
do,
tension zero, right?
yeah, tension zero. Because the material has some hysteresis. So if we reload to the displacement equal to 0, because there's some residual strain, residual strain, so they will become a little compression. So it become buckle. Some example become buckles. Yes.
Correct. And I think the part of your bias may be due to that. So another way to think about this is instead of doing tension back to stretch to 1, then tension back to, you can do maybe 1.7 to 1.1, 1 point something. Okay, so you keep your specimen under tension all the time.
Yes.
That may avoid some of the bias. Okay.
Right. It could be one reason for the bias. Yes.
Right.
Thank you.
Right.
Yeah.
And you mentioned ceramics as a potential material. Certainly, metal fatigue has been done for a long time, but there's also this phenomena. If you have consistently tension fatigue, so you have for metal fatigue, certainly you have the amplitude and you have the R value, the maximum over minimum value,
Yes.
or minimum over maximum value. Sometimes that value for metal can even be negative, but in this case, negative is not allowed.
Yes.
When you have tension fatigue, in some of these materials, you would also see ratcheting, meaning that even as your this is under controlled load fatigue, even if your loading amplitude and the maximum minimum loading remains the same, the deformation keeps increasing, ratcheting. Okay. In the displacement controlled case, what could happen is you mentioned that there are hysteresis, right? What could happen is as you do constant displacement cyclic loading, the system relaxes over time. So that may be another thing that you probably want to look into.
Mm-hmm. Yeah, thank you. Yes.
Okay. Yeah, that's my comments, but very interesting work.
Okay. Yeah. Thank you, Jamie. I got a point. Yeah. Thank you.
Yeah. Okay. Tongqing, can you unshare your screen?
Yeah.
Changhui is next. Changhui, before you ask a question, can you introduce yourself? Where do you work?
Okay. Thank you, Zhigang. Hi, everyone. This is Changhui Yang from Southern University of Science and Technology. So before joining SASTEC, I was a postdoc in Zhigang's group as well. So currently, I have been working on mechanics of soft materials and stretchable. We call it ionotronics. It's basically a family of devices using ionic conductors as the charge carriers. Okay, yeah. All right. Yeah. Hi, Tongqing. Thank you for the wonderful talk. This is the first time I hear your so systematic work on this high throughput experiment. So I have a small question about the random variable scatters. You compare the scatters of between ceramics and rubbers, but you choose to use the strength of ceramics, but stretchability of rubbers. So what's the rationale of choosing strength or stretch as the variable? And yeah, if you, for example, if you choose strength of rubber to calculate this scatter, will this scatter increase?
Okay. Thank you. Changhui. Good question. So, yeah, because in this example, I showed the comparison between strength of ceramics and rupture stretch of silicon rubber, because we happen to have these two data sets. That's the reason. That's the reason. Because in literature, we find the data for strength, but for our own experiment, we only have the data for rupture stretch. Okay, so if we change, for example, the rupture stretch to strength of rubbers, of course, the comparison could be different. But the point is here, we just want to point out for different materials or for different, so strength and the stretch itself also is different, may have different scatter probability, property. Yes, so we just as an example, so we cannot directly compare the stress of stretch, of course. Yeah, they're just just the two examples because we happen to have these two data sets.
Okay, yeah, thank you.
Yeah, thank you.
So next, Beijing Shen. Yeah, can you please introduce yourself before you ask question?
Thank you, Professor Sauce, for picking me up. Hi, everyone. My name is Beijing Shen. I'm from Johns Hopkins University. I'm currently 5th-year PhD student working with Professor Vicky Wen. And thank you, Professor Lu, for a very fascinating talk and very interesting about your content. But actually, I have very specific technical question about how did you basically load your sample and unload your sample? Basically, how did you attach your sample to your customized setup? And when the experiment is done, how did you basically move it out? So I'm assuming that you are not basically manually load every sample individually to the setup, right? All right. Yeah, that's my question.
Okay. Thank you. Oh, I didn't explain the details. So in the first generation of our experimental setup, so the samples are prepared using 3D printer. So the 3D printer just print the connection region as well as the samples together. So when we print, we print all the 5 rows, So we only need to clap the 2 ends of the 5 rows and stretch the whole thing. Yeah. So of course we cannot do manually one by one because that's not high throughput. Yeah.
All right, I see. Thank you.
All right. Okay, next up, Zhigang Suo. Zhigang Suo, please introduce yourself and ask question.
Thank you, Zhigang. My name is Zhigang Suo. I'm an assistant professor at Northwestern University. Thank you so much, Tongqing. It was a great talk. I really enjoyed it. My question is more about material science point of view. So you introduced 2 ways to characterize the fatigue. One is SN, another one is crack growth. And you also have the data from 2 methods. Do they measure the same thing or do they measure a different thing? For example, if I develop a material, the features of the materials differently affect each one of it. So I was wondering, you are measuring the same thing with 2 different things, or you are measuring 2 separate things with 2 separate experimental tools? That's the main question. And the comment is that I think you can apply various stretches by designing the machine. For example, you can put different initial length and apply the same displacement to apply the different stretches at the same time. Or you can use you can redesign how can I say that this structure, so that
That's true. Yeah.
first column, second column, third column stretch differently at the same time. I think it would save your time a lot. So that's the comment. Thank you so much.
Yeah, thank you very much. Yeah, very, very good idea. Actually, the student Yifan Zhou, who has already graduated to industry, he also proposed the similar idea. For example, the different initial lengths or the different displacement between the rows. Okay, anyway, maybe in future we will try that for some purposes. And for your question, the two kinds of fatigue test to characterize the same thing or different thing. Okay, that's a very big question. Maybe Zhigang has a better answer. Yeah, because I learned this part following Zhigang's notes on fracture mechanics. So the answer reading the notes is that if you measure S-N curve or lambda N curve, because you do not introduce any pre-cut, so the natural flaws may influence the results. And the natural flaw, of course, you cannot control. So yeah, that's one thing. So you can see a lot of scatter. So for the lambda N curve, because each example they have different flaws, different defects. The other thing is this approach has been widely used in industry in practical application. Yeah, because it's simple. But in industry application, people usually do different S-N curve. For example, tension bending S-N curves or something like that. Yeah. And for the GED-CDN curve, then in this characterization, actually we use the fracture mechanics theory. Yeah. So we use the concept of energy release rate, and we make a pre-cut to shade all the effects of other small natural flaws. And in principle, this GED-CDN curve, you can predict some behavior on the S-N curve. So at this point, these two methods are consistent. But there's some other factors. They are not reflecting different things. They're focusing on different things. Yeah. Thank you.
Thanks.
Okay, Jiawei, please introduce yourself, ask question.
Hi, everyone. I'm Jiawei Yang. I'm a long-term EML follower. So I'm a new assistant professor in WPI. Our lab is working on multi-scale engineering of software materials, mainly for healthcare and sustainability applications. So yeah, so the question here. So I have two questions. One is more technical. It's about p-value. So in general, you just say if p-value is bigger or p-value is smaller, but is there any cutoff? I mean, in biology, people use p is 0.5. So is this the same case apply in your situation?
Okay, yeah, thank you. Because we learned this test method from the Stanford group. Yeah, they told us actually the number of p-values, the absolute number. There's no general standard for which number is a standard. So it depends on your application. It depends on the application. For example, for some tests, maybe 0.1 is good enough. What means good? It depends on your requirements. For example, if you feel your results satisfy your application, you maybe say 0.1 is good enough. But for other applications, maybe p equal to 0.5 is good. So there's no standard, but there's comparison. For example, the old setup and the new setup, the p-values are much different. Yes.
So in your case, you just set p is 0.5.
No. We maybe we just set p equal to 0.1. We say if it's bigger than 0.1, then we say it's good. And all the values are larger than 0.1. Yeah.
Great. Yeah. So the second one question is about the material types for high throughput experiments. But in your case, you can do 3D printing or laser cutting to create all different, thousands of materials, right? So if some material cannot be laser cut or 3D printed, how do you do that? For example, ceramic, probably you cannot use using laser cut.
Yeah. Currently, we cannot do that hard materials.
But even for hydrogels, probably it's also not easy to make a big piece that you cut, right?
Yes, hydrogels, actually, we did have a try. Because the laser cutting, we introduced some actual heat to influence the property of the hydrogel. So finally, we gave up. So for the sample preparation, of course, there's many advancing or developing method. We do not specially develop that part. Yeah, we just use the existing one in our lab. Okay.
Yeah, I think there's another advantage by doing this is because soft materials like elastomers and hydrogels, like you always can change their properties by adding fillers like nanoparticles or change cross linkers. So is that possible? You can load hydrogels or elastomers or different chemical formulations or compositions, so you can simultaneously test how this modification affects the mechanical properties. That will be very efficient and helpful.
Yes, very good idea. That's what we are doing right now.
Perfect. Thank you. Thank you. Very interesting talk. Thank you.
Thank you.
All right. Next up, Ray, please introduce yourself. Ask question.
Okay. Thank you, Zhigang. Thank you. My name is Ray Huang. I'm the UT working on mechanics of soft materials and some other materials too. Tongqing, thank you. Nice to see you here. Let's see. Very impressive work. I think I have a comment, maybe a small question. One is about this. Zhigang mentioned these different kinds of throughput experiments. I think my experience is there are some of these experiments. I remember some years ago at NIST, somebody were trying to develop this high throughput, as they call it, combinatorial testing. Chris Stafford, who had a paper on how to measure just thin film modulus. So they use a wrinkling method, but they can generate a lot of specimens in time using some optical method. So that's I think NIST is place they want to develop this kind of high throughput experiment for various properties. The other area, I think, of course, in ceramics, right? So when we measure the strengths, usually the simple test is 3-point bending, measuring the so-called fracture strength. So people know that that measurement is highly statistical. So they have to test many specimens and fit it with Y-body distribution, that kind of thing. I don't know if they can do high throughput like you did with simultaneously, right? But they do have to collect a lot of data, maybe very time consuming. Not sure if they can adopt this idea doing high throughput more efficiently. The other area, also very important area, I think Zhigang also mentioned the electronics, especially in microelectronics. One kind of experiments is electromigration reliability. So there, indeed, as I said, they care so much about rare events at the tail of distribution, because that's where they need to make sure it's high yield. So they want to yield in basically these are circuits, right? So they have to be yield more than 99% has to be good. So they cannot afford any high failure or issues. So I think that in that industry, it's well known. People have to do this large number of experiments. There's a concept I don't actually know very well called daisy chain. Basically, they link up all these lines, like in series. They run the current through and then measure all these lines simultaneously, which one start to fail first, and then they do a statistical analysis, that kind of thing. So that is one area that I've heard about it. So certainly there's a lot of interest, I think, if you want to make this material or device into practical applications, high yield and these very advanced statistics could be very, very important. Now, finally, my question. I think at the end of your test presentation, you mentioned the fracture test with the pre-cut. There you say maybe it's enough to have only 10 specimens. So I wonder, is the statistics different once you introduce a pre-cut?
The statistic.
Yeah, so basically, previously without pre-cut, right? So you said we may need 100 or 1,000 specimens to get a statistically, correct or reliable. Now, if we make a pre-cut, I think in one of your setup, you have different cut size, right? So you have a specimen. But I'm wondering, for each cut size, do you need to, how many specimens do you have to do to making sure you get the correct or reliable statistics?
Okay, thank you, Ray. First, thank you for introducing the other areas of some similar work. We also noticed some of them. For your question, actually, it's a really good question because it's the ongoing work in our next paper. Actually, we already have some results. I didn't report in today's presentation. So because in today's presentation, we make pre-cut because we do fatigue tests. Because fatigue tests, even in high throughput, is time consuming. So if we investigate the statistic introduced by different pre-cut lengths, we have already done experiment for to measure toughness, not fatigue, because you only stretch it until rupture very quickly. So you can do lots of samples. And also we use the statistic method, as I just mentioned, called the bootstrap method, to calculate the toughness interval. And our results show that only for the single edge notch specimen with different pre-cut, we first prepare, for example, 50 or 100 samples with the same pre-cut, and see if the measured toughness converged or if the confidence interval is narrow enough. The results is it's converged. The confidence interval very narrow.
In the sense the scattering is very narrow.
Yeah, very narrow. And also we tested if we put different pre-cut lenses. We also use the little formula to calculate the toughness. The results also shows a very narrow confidence interval. So that means the method to introduce pre-cut to measure the toughness is really a stable, a reliable method. Yeah, at least for the material we tested. Yes.
Thank you.
Thank you.
Chang Hong.
Yes,
introduce yourself and ask question.
Okay, thank you, Professor. Hi everyone, my name is Tongqing Lu, and currently I'm a research fellow at Nanyang Technological University, working with Prof. Jamie Xiang and Prof. Jian Gao. So Prof. Lu, thank you very much for your interesting report. It's quite new to me. I learned something new here. So my question is about the preparation of the sample and the installation of the sample onto the clamp. So even for the testing of a single sample, I think there are some side effects on the sample geometry. I see for your uniaxial tension test, the sample are very narrow strips arranged in very dense, a very dense way. So my question is, will the geometry of the sample and the way you arrange the installation of the sample will influence your results? And are there any rules or standards about this?
You mean the simple edge notch specimen?
No. I mean the simple, the specimen. The geometry of the specimen and how you install it onto your testing machine. How dense? What's the distance between the samples?
Okay, the distance between the samples. Okay, the width of the sample is 0.5 millimeter.
Yeah,
and the distance, I cannot remember, but it's of the same order of the width.
Yeah. So my question is, will the
millimeter.
geometry and those geometries influence the results? And are there any standards for those selection of the geometries?
Yeah, we have not investigated the effects of geometry. Yeah, we have not. Yeah.
Do you have any comments on this? I think even for a single
Because this
next
kind
extension.
of experiment, high throughput experiment, were new. So maybe there's no so-called standards. Yeah, of course we can try to see if there's effects. Of course, geometry effect could be important to affect the final results.
Maybe let me point out one particular geometrical effect, potential aspect ratio. When you have different length to width ratio, you may have slightly different results.
Oh, yes. Oh, I just remember, actually, we have tried with different lengths. Because we may think with a longer length, maybe there's a larger defect or different weights. But the results does not look like what we expected, because the material is what we printed. So the printing material have some anisotropy. So it's not an isotropic material actually. So this geometric effect could be a little more complicated. So then we gave up to study this effect. It all depends on how you prepare samples actually. Yes. Thank you.
Okay, Ke Jie, introduce yourself, ask question.
Oh, I thought Jingda was before me, but I can go first. Good morning, everyone. I'm from West Lafayette. This is the morning time. My name is KG Zhang. It's great to see Tongqing and great to see everyone. Many good friends here. I'm a faculty here at the Purdue University in mechanical engineering. I don't particularly work on software material, but I have a very keen interest in this area, and I studied different angles of interest actually. So first, I have a question. I think perhaps I asked the same question as many has already asked, but I want to ask in my own way. So first of all, about this high throughput experiments, as Zhigang commented, there are not much high throughput mechanical experiments as compared in chemistry, like electronics. I feel it's just because in mechanical field, there's not much variation. Like if you measure the mechanical property, measure the homogeneous material, why we need a high throughput experiments, right? But in Tongqing's, this is exceptional, that this fatigue is very sensitive to many factors, as Tongqing pointed out. So then my question is, what do we learn here from the high throughput experiments, right? So I think Jiang and Robin asked this essentially kind of similar question, that do we learn something intrinsic property or material behavior from high throughput? I can understand that Tongqing highlighted using the high throughput experiments can be used to calibrate the experiments, which is great. Then they can improve different generation of this apparatus and to reduce the uncertainty. But do we learn something intrinsic material property? For instance, you mentioned the flaw sensitivity. To me, this is a kind of unfamiliar word. I know flaw. What does flaw mean in ceramics or metals? What does flaw mean in soft material? What kind of flaw we're talking about? And then Tongqing mentioned that there's uncertainty will significantly reduced if they have pre-cut. I guess because you introduce a major flaw there, right? So then statistically the experiment data become so much better. But in this lambda n measurements, what kind of flaws here are there? Is it kind of statistics that come from this intrinsic flaw, or is simply because of different batch of samples? So this is the one kind of similar to the similar question, what do we learn from the high throughput experiments is, I feel when I first see the lambda n test, I feel, oh, this is a fatigue law, right? We can easily fit the fatigue law. And then Tongqing mentioned that then we can use this to predict the rare events. Then I was stuck on this. I feel this is so important, but it's kind of also aggressive in rare events prediction, given so many uncertainties at this point. So are those rare events are really the bad sample, or is it really the rare events in reality? So this is my first question. I will come up with a second question. The other question is rather more naive, but I will come up next to the question later. So I want to Tongqing to comment. What do we learn from here from high throughput experiments?
Okay. Okay. I think maybe at this stage, we just start to establish this method, and because for example, we use some statistical method to guarantee our high throughput experiment output some reliable data. So actually, at this stage, I think it's just a step for establishing a reliable method. And next, actually, what we are doing, we are trying to use this setup or use this method to learn something new. Yeah. For example, I forgot who mentioned that, maybe Jiawei. For example, if you want to, your question is about the lambda n curve. So the Jiawei's question, if you can change the material composition to see some maybe mapping relation between the material and the material composition to the mechanical property. So this is what we are going to do, or something we are doing. So we want to use this method, this setup to learn new things. But for the lambda n curve, actually, I didn't I haven't thought this this far. Thank you. I will think about it. Yeah.
Perhaps, I give some thought. I mainly learn things from Tongqing. So maybe paraphrase Keji's question. The question could be, now we can do high throughput experiment.
Right.
What can we learn in the future? Not necessarily Tongqing, what have you learned? Tongqing probably haven't learned much, but what can we really learn? Because the new tools are being made available. For example, 3D printing easily allow you to print a large number of samples in parallel, right? And also, Tongqing didn't quite mention that, but he and his student did a lot of work, the imaging. Because if you have thousands of samples, you cannot ask a student to watch videos and identify which sample failed at what time. So the student actually did a program to do imaging analysis. So the computer automatically report which sample failed at what time. The third thing is Tongqing keep mentioning we have a Stanford group working with us about a statistic. Actually, mostly importantly, Tongqing didn't talk about was machine learning itself. So one to analyze data, one thing Tongqing is working on in this collaboration is to ask the question: how do we test the material? When you test the material, there are so many other variables. For example, composition, arrangement, microstructure. Now you can control. How do you go through from a sample preparation with a large number of parameters you can vary, and the property space, because we want to push the envelope of a property space in Ashby map, that sense. Then clearly, if you can parallel do large quantity of samples, clearly you can sample a lot of samples. So in the material development, with machine learning in the loop, you can possibly design an experiment very efficiently, almost like combinatorial chemistry, but now with the mechanics and the geometry as a variable.
Yeah, I feel this is something paradigm shift. It could be in terms of compared to the traditional thinking of the mechanical test. So Tongqing's answer is very modest. I fully agree, and Zhigang's answer is very visionary. So I think it's a combination of these two answers really really helped to understand what is the long-term goal and what do we learn. This is great.
Can I make a comment on that as well?
Of course. Yeah,
Yeah.
of course, yeah.
You made the point very well that many of the mechanical properties we measure have very limited scattering. For example, yield strength. Actually, for a material, if you measure yield strength of that material, or a group of material, or a specific material, you cut the sample to different sizes and you measure it, you pretty much get the same results. But other properties may not be. For example, ultimate strength or ductility. These failure-related material properties, they actually have a lot of scattering, going all the way back to Griffith. When he tested glass, he had huge amount of scattering. So that aspect, I think the Zhang actually did some work on that, the statistics, but very few in the community actually appreciated that aspect enough, I would say. Yeah. So
absolutely.
The plus and minus, you are right for certain properties, but other properties, statistics or high throughput type of experiment may be useful.
Yeah, absolutely. This is what the young generation can always learn from Jimmy and Zhigang, right? What is the vision of this field and what we can do with this new methodology, new development. I think this is a great.
Could you have a question?
Yeah, I have another question. If I'm not taking too long, so actually this is a quite naive question. So because I learned so much from Zhigang's group about rubber, elastomer, right? Now I work on new different polymers for mostly chemically active polymers. They can pass the current and they use a device for windows and for transistors and for biological applications. And then people want to understand what is the mechanical behavior. They see mechanical failure. But then they come to me and, hey, can you help me to understand this mechanical behavior? It's totally different polymer. I never heard of those polymer. Like some polymers may be similar, like a highly entangled polymer. And then the first thing is I look up what is constitutive law, right? Otherwise, I cannot even do FEA modeling. Then I couldn't find any. I'm just wondering why do our mechanics people don't study those polymers rather than just focus on rubbers? Those probably are well known, I guess. Why don't we study those like a heterogeneous polymer, for instance, and multi-component polymer? What is the state of the art in terms of constitutive law description of those polymers? Okay, Tongqing or anyone want to share some insights? Because I really don't. I try to find literature, it's just very few. And if we want to do by ourselves, it's very difficult for us because we don't have facility, we don't have people. So yeah, what is I guess my summary of my question is, what is kind of the state of the art of constitutive law in terms of those polymer materials, like especially for highly entangled polymer?
Yeah, I'll give a try. Ke, you ask a question people have asked for many decades. In the field, it's called a rheology. They don't call it a constitutive law. Rheology.
Okay.
Right. It's generally if you give us a history of stress, what is a history of strain? Is it in one form? The question doesn't have a general answer. Materials are different. Right, you have to limit your ambition to a more specific question. In general, yeah, it's nearly hopeless.
Okay. Yeah. Then where should I start from? For instance, I have polymer P.PSS, right? Has been in the market for a long time, and then when I published the first paper, I just used the new Hooking law, and obviously people say that's not right. Then what is it right? So where do I start from if I want to test P.PSS?
P.PSS is a thermoplastic, right? It's not rubbery.
It has the two components polymer, and it has right. People use it for mixed conductor, basically. So, but if you want to describe I'm sorry if my question has been deviated from Tongqing's topic. This is just again, this is just my own naive question. I can forget about it. I can have a discussion.
No, but could you just try me? You can go to Vicky's or Jerry's, Mary Boyce's previous work. You must be familiar with some of them, right? Some Spring dashpot model and
Yeah.
more physical model.
Right.
Some of them work pretty well. It's just complicated.
It's just this entanglement, right? The feature is this high entanglement. Is there any mod considered good for highly entangled polymer?
I don't know. My understanding is you put a few springs and dashpot and then sorry, we're streaming. So I should
to explore on his own. So Matt, please introduce yourself, ask question.
Hi everybody, my name is Matthew. I'm a postdoc at Zhigang Suo, and after 2 years I returned back to Nanyang Technological University as an assistant professor after 2 years. So my question is so actually two questions. Actually Zhigang actually answered one of it, which is how do you actually detect the rupture or even the crack growth of you have so many samples, how do you actually detect the rupture and the crack growth? So I think Zhigang answered that it was a program that actually used the image, but I assume that for crack growth of materials, especially since you went to pure shear mode that was presented later on, how do you actually measure pure shear and crack growth at high resolutions?
The crack growth in high resolution,
Yeah, for each, because you have so many samples, right? You have to measure crack growth for each.
Yes. Yeah, just use image processing. Of course, the resolution thing is a very important thing. We need to control the size of the sample, and with our condition of the resolution of our camera. Yeah, you need to match them to record this crack growth. Yes.
Yeah, and I have one more comment or rather question is, increasingly machine learning is becoming much more popular, especially in material science, to predict properties of soft materials or any kind of material. So is this high throughput experimental procedure that you have done competitive to machine learning, or can there be some sort of synergy between the two that can be used in the future?
Yeah, the machine learning, actually, you need to some input data, and then you train something and learn something, right? So this the high throughput experiment method actually just generate data. So the generated data, of course, can be combined with the existing so many machine learning models, and to train and predict something else. Yeah, that's what we are trying to do. Yeah. Yeah, if you combine these two, it will be much more powerful, I think. Yes.
Tongqing is very modest. He is writing a very exciting paper now. My machine learning and high throughput experiment.
I look forward to reading that.
Yeah, thank you.
Yeah. Jinda, please introduce yourself, ask question.
Hi, everyone. So I'm Jingda Tang. I'm from the same university as Tongqing Jiaotong University. We are colleagues. So my question is similar to Jimmy and Kejie. So for the fatigue part, so the fatigue property of rubber of elastomer has very large scatters. So the high throughput test may be permissive for testing these materials. So can you use the method to test some classical materials and get some new conclusion? Because in the history literature, the scatter for the fatigue threshold of natural rubber, maybe other rubbers is large. So maybe this can provide this method some advantage. So and show people some new conclusion. So now you always so now you use the as prepared material in our life. So can you use some classical product material to do this?
Classical means some commercial
maybe
materials.
Yeah, commercial natural rubber, something like that.
Yeah, actually, yeah, in principle we can. Yeah, the problem is still in the massive sample preparation. If we have a good way to massively prepare the samples made of the material you mentioned, like natural rubber, we can do that.
That's my second question. My second question is, so now the mechanical test for the report test is very fast, but the time for preparing the sample is very long. So how do you solve this problem?
Yeah, in all the existing works, the preparation time is not long. 3D printing is very fast. A laser cutter is also very fast. So yeah, some other people also mentioned the question, but this limited to some materials. Yeah. If you want to change, yeah, like what you said, some natural rubber or some classical materials, we need to develop some new sample preparation method, yes, to reduce the time of this.
Okay.
Yeah, I'll give you one example. Tongqing and I and other students are talking about. For example, for polyethylene, classical material, right? Polyethylene.
Yes.
If you buy a large sheet of polyethylene, and then you just use laser cutter to create large number of samples, they're all connected. You can test them.
Okay.
Right? Yeah, it just as an example. So yeah, high throughput experiment itself require lots of ingenuity for development. That's true. It's because we don't have a lot of experience in the field. All right, Zhenjin, please introduce yourself and ask question.
Hello, Zhigang. So happy to see you again, and Jimmy and other friends. I'm Zhenjin Wang from Xi'an Jiaotong University. I'm also just in the same lab with Tongqing. And before I went back to China, actually, I stayed in Zhigang group for more than 6 years as a visiting PhD student and a postdoc. And currently, actually, in my group, we are doing some dynamic behavior of the soft materials. We are trying to develop the stimulant of our body and to simulate the damage of our body and the dynamic loading, like a car crash or even the bullet is kind of impacting things. As Zhigang just mentioned before, the seminar is that because actually now in our lab we are so many young people just with a similar background. Actually, we are trying to do something different to differentiate ourselves. So like Tongqing, even we spent a lot of time together, and actually this is the first time I just listened to your works in such a detail. Actually, I have one technical question that about the setup in your first and second generation that uses the displacement control. Actually, we know that it's kind of easier to achieve that. What I'm interested in that in your third generation, you can measure the stress actually individually. How did you achieve that? Just putting so many load cells in parallel? That's my question.
Okay. Yeah. To measure stress, actually, Wu Hou invented this method. So you just for each example, you just put a force sensor in series with the sample, but the sensor is not the commercial sensor. The sensor is just calibrated soft materials. So you first calibrate the stress strain curve of this material, and then you just put them in series. So when you stretch it, you also measure the strain or the stretch of the force sensor, and then convert to stress. Yeah.
Okay, got it.
When you fabricate this massively fabricate the examples, the force sensor material can be also massively fabricated. Then it will not influence the result. Yes.
Oh, okay, got it. But in that way, actually, we like just in one row, you stretch like it's kind of you say the load sensor and the material tested in series, and
Yes.
in that way, actually, since the material is neither in force control or no displacement control. That is even just because if the stress is different, the strain and also the different for individual displacement. I know that you can just because identify it just by your image just one by one. Is that right?
Yes, it's not load control or displacement control, but we can measure the stress and strain simultaneously. Yeah, that's the goal. Yes. Thank you.
Yeah, that's my question. Thank you.
Okay, Chen, please introduce yourself.
Yeah, thank you, Tongqing, for your wonderful talk. So this is Zheng from Zhigang University. I'm also working on mechanics of soft materials in recent years. And so I have two very quick questions. The first one is, when we do the fracture test, we want a sample to fracture in the middle portion of the sample. And in your experiments, in the videos, I do see some samples, they fracture somewhere very close to the fixture. So I wonder, did you consider those samples as effective, or I mean the origin of the bias? So that's my first question. My second question is, did you ever estimate the largest number of samples you can test in one single test? So because I think you cannot make a sample which is too large. Otherwise, you don't have a loading machine to load it, or you don't have a 3D printer to print a sample which is too large. Yeah, so these two are my questions.
Okay. Yeah, thank you, Zhang. For the first question, we do not study the failure position of each individual sample. Yeah, we do not. But we found that most of the samples fracture at some middle part of the sample. So we feel it's okay. Of course, we can specially investigate this problem. The second thing is, yes, we cannot make as much as we want. The first limitation is about the loading. The second is about imaging. Yeah, and the third, as you mentioned, is about the 3D printing. So all the three parts, the sample preparation, loading, and imaging will have the restrictions on how many samples we can test. Yeah, but each of them can be improved, of course. Yes, thank you.
Thank you.
All right, Zomarat?
Yes, hello everyone. Sorry, my camera is not working today. My name is Zumrad Usmanova, and I'm a second-year PhD student working with Professor Robin Bai at Northeastern University. It's a great talk, and it's actually super amazing that we're trying to create this high throughput experiments. And I know it's probably there's like a lot of technical difficulties associated with that. And that's actually like my question to one of the follow-up questions is like, how reliable is the experimental setup? Because like normally if you would do like this high throughput experiments, for metals, for example, like your material is rigid enough, so you don't need to worry about the sagging or any like the aspect ratio. But in the case of rubbers and elastomers and soft materials, I think it's a bit more tricky. So have you like looked at that like aspect ratio effect of the machine, since like your entire setup is not vertical, it's horizontal. So I'm assuming if your sample is like thin and long enough, it would be much more tricky to perform the tensile test on it. Like, have you looked at that effect?
Okay, so your question is mainly on the aspect ratio of the sample. Yeah. Okay, we have not investigated this effect. As I said, we have tried the different weights or different lengths. We try to see if there's some effect, but eventually you find that because it's 3D printed material, and I thought an anisotropic effect dominate the property. So we do not see any other geometric effect. So yeah, we may have a try in the future.
Also, like
for the current results, as we said, by some statistical method, we can confirm that the repeatability of each round of experiment is good. Yeah, that's what we can say.
Yeah, also like a follow-up question to that. So like normally we would have like some kind of ASTM standard for like the size and the shape of the material when we're performing certain tests. I'm assuming here, are you still following the same, like say the size standards for the sample? Because you have like thousands of samples, you need to make them really small to actually perform like that large of an experiment. Like decreasing the size of the sample, does it like decrease the reliability of the test, or like have you also tested that?
Okay, we have tested that. For example, we can measure stress and strain in our new setup. So we can measure stress strain curve from our high throughput experiment, and we can do a standard test using the standard tensor machine, use some ASTM standard, and then we can compare stress strain curve from our high throughput experiment and the standard test just for one specimen. They are close enough. Yeah, we find that they are close enough.
Okay, thank you.
Thank you.
All right. So Jimmy, do you have some closing wisdom?
No. We usually give it to Zheng because he's now the leading person for the EML webinars. So maybe he can make some comments.
Okay.
Yeah, thank you, Jimmy and Zhigang. So can you see my slides?
Yes.
Yeah, I just want to make a quick announcement that so the next two EML webinar Young Researchers Forum will be given by Professor Mingchao Liu and from the University of Birmingham and Professor Evgeny from University of Michigan. They are both the recipients of the 2023 EML Young Investigator Award. The next EML webinar will be given by Ming Chao. So the time will be in May, so next month. So please stay tuned. Thank you.
Thank you.
Thank you.
Okay. So I guess this will be end this webinar. Tongqing, thank you very much. You get people excited about high throughput experiment.
Thank you.
Thank you.
Okay.
Thank you.
Thank you, Tongqing. Bye.
Bye-bye.
Bye-bye.
Bye.
Bye.